Have you ever wondered just how special you are? I don't mean like being your friend's best friend or the chess champion of your neighborhood. I'm talking about being truly unique on a cosmic scale. Look in the mirror. Yeah, that's you. From your perspective, just an average person. But if you look at yourself through the eyes of the stars, you're a walking anomaly. But why? Because our planet isn't just a cozy little apartment floating in space. It's such a rare and strange phenomenon that if the universe held a quiz called Find a Planet Like This, there wouldn't be a correct answer. Take a look around. Everything you see is the result of a billion coincidences. Or is it? Why, out of the endless stars and planets, did we end up right here on this tiny blue dot? Today, we're uncovering secrets that will flip your view of the universe. You'll learn what makes Earth so extraordinary, why most star systems are breeding grounds for instability, making life like ours impossible nearby, and how human civilization might be the greatest anomaly in the universe. This episode isn't just about stars and galaxies. It's about what makes us, us. And maybe it'll leave you with a quiet, almost eerie sense of loneliness in the vastness of the universe. Stick with us as we uncover jaw-dropping secrets that could completely change how you see the cosmos.
1, 2, CogniQ.
Let's start with something simple. You've probably heard this popular idea. Everything in nature strives for symmetry. Ice, snowflakes, frosty window patterns. These are supposedly proof that nature loves order, but that's not quite true. In fact, a crystal isn't about creating symmetry, it's about breaking it. Yes, you heard that right. Liquid water is actually more symmetrical because its molecules can move freely, taking on any position without being stuck in a rigid structure. When water freezes, its molecules line up into beautiful, intricate patterns. Looks amazing, doesn't it? But here's the catch. This isn't true symmetry. It's a rigid structure created by losing uniformity. The same thing happens with salt crystals. Ions that were floating around randomly in a solution suddenly snap into a neat, organized lattice. And nature is full of millions of examples like this. What's fascinating is that even in what seems like chaos or destruction, there's a hidden order, a structure or logic that governs how things evolve, even if it's not obvious at first. And this order shapes everything we see around us. Think about how traffic flows smoothly during rush hour, guided by unwritten social rules, or how galaxies naturally arrange themselves across the vastness of space. What's behind these symmetries and disruptions? Stay with us. There's so much more to discover. We know why water turns into ice or steam. We understand how remarkable stars and galaxies are born. But do you know what we don't understand? Why we exist. The universe is the worst place for life. It's cold, empty, and deadly. Is there any planet, besides Earth, where we could live without a spacesuit? So far, the answer is no. Scientists Peter Ward and Donald Brownlee call our planet a phenomenon. They argue that complex life is an incredibly rare occurrence. The conditions that allowed us to exist could have only come together once in the entire history of the universe. And that's what their book Rare Earth is all about. It's the foundation for this video. But are we really unique? Or is it just another illusion? Let's take a closer look. Many people think of Earth as just another ordinary planet among thousands of others. We're a tiny speck, lost in the vastness of space. Carl Sagan and Frank Drake, along with many other scientists, argued that Earth was merely one of many ordinary rocky planets within typical star systems. These systems are scattered throughout the unremarkable regions of the vast universe. They believed that, because Earth seemed so ordinary, there must be countless other habitable planets elsewhere. This perspective became widely known as the principle of mediocrity. What if Earth isn't just one of countless planets out there? What if it's something truly unique? What if our solar system is unlike most others, but an incredibly rare setup? And maybe, just maybe, even our galaxy isn't as ordinary as it seems. We're not just the result of random chance. Our planet isn't just a rock among the stars. We're the exception. And most likely, in this immense universe, there's truly nothing comparable to us. How did all these circumstances align to make us who we are? Why does humanity exist? Let's take a closer look at our planet and solar system. You'll be amazed by what we uncover. According to proponents of the rare Earth hypothesis, planetary systems capable of supporting complex life must closely resemble our solar system. For life to exist on a planet, it must lie within the so-called Goldilocks zone, also known as the habitable zone. This zone refers to the area around a star where the temperature and surface conditions of a planet allow water to exist in liquid form. And water is the key element for life because it dissolves substances necessary for biochemical reactions. Earth is not just in the right zone. Its behavior within the solar system is perfectly tuned for supporting life. Our planet's orbit around the sun is almost circular, which means we never get too close or too far from our star. And many scientists claim that if we discover rocky planets within the habitable zone, life on them might be almost inevitable. But soon you'll see that this isn't enough for life to thrive. In truth, much rarer conditions are needed. What if I say that our planet is not just in the perfect zone of the sun, but in a zone that makes it unique for the entire galaxy? It sounds incredible, but the authors of the unique Earth theory argue exactly that. They believe that Earth is not just well-positioned relative to its star, but even more surprisingly, it lies in a life-friendly part of the entire galaxy. It's this position of the solar system in the galaxy that allows you, me, and even your neighbor's overly enthusiastic dog to exist. The solar system makes a complete journey around the center of our galaxy every 230 million years. This means that since the oceans appeared on Earth, it has traveled this path 17 times. And since multicellular life emerged, it has completed 7 full rotations. But this is not just a simple journey. The galaxy is full of threats that could erase us completely in seconds. And all of this happens over immense spans of time. But even so, you're still watching this video. I'm already working on the next one, and I truly hope you've subscribed to the channel and clicked the like button. The galaxy is full of dead zones where life is simply impossible. The deeper you go into the galaxy, the more threats you encounter. Black holes, neutron stars, powerful gamma and X-ray radiation. The closer you get to the center, the more frequent the supernova explosions. They devastate their surroundings, and that's just a small part of the nightmare. One might think that the more stars there are, the more chances there are for life. But in reality, most stars are concentrated around the center of the galaxy. That's where the real cosmic meat grinder happens. Gravitational disturbances and the high density of stars pose a significant threat. Even if a planet is in the perfect zone, the close pass of another star can disturb everything with a single movement. But being too far from the center is no solution either. Stars lose the required metallicity, and metals are essential for forming Earth-like planets. Recent studies show that the zone suitable for life in the galaxy is limited to from 7 to 9 kiloparsecs from its center, which equals approximately 22.83 to 29.35 light-years. That's only 10% of the stars in the Milky Way. But even more interesting is that for life to emerge, only about 5% of stars are suitable. But here's the kicker: time. By the way, I dropped a pretty cool video on this topic already. If you missed it, do yourself a favor and slot it into your evening binge watch session. Now back to the point. For life to even have a shot at evolving on a planet, its star needs to maintain stable conditions for billions of years. I mean, the star's orbit has to be almost perfectly circular and stable. No frequent joyrides through dense star clusters or, as the science nerds call it, spiral arms. Earth found itself in a unique position, both in the habitable zone of our star and, additionally, in the galaxy's own habitable zone. But wait, there's more. Our Milky Way is like that one unbothered superstar at a cosmic gala, a rare gem of the infinite cosmos. In 10 billion years, it hasn't bumped into another galaxy even once. That's why it is so quiet and dim. Only 7% of galaxies are like this. Even on such unimaginable scales, there are many factors that determine our uniqueness. But most of these cosmic coincidences are hidden not out there, but right here in our solar system. When we look at stars, they seem like just bright dots in the sky. What if we got closer? Would it be just like ours? A sun? Planets? Life? Well, not exactly. More than 50% of stars in our galaxy are in pairs. So if you traveled to one, you might see 2 stars instead of 1, or even 3. For example, the North Star, a guide for travelers seeking the North, is actually a triple star system. Imagine gazing upon that stunning beauty with your own eyes. What an unforgettable sight it would be. Binary, triple, and other cosmic clubs sounds cool, right? But in reality, these systems are almost always completely unsuitable for life. The orbits of planets in such systems are like fighting a bear in Texas. It could end very quickly and probably not in your favor. For even a lifeless planet to exist among such hotshots, its orbit would need to be perfectly tuned, or it would require truly extraordinary conditions. I'll say it again, more than half of the stars in star systems, just know they're completely empty. This is just the beginning. Have you ever thought about this? Our sun isn't just a star. It's an exception among billions. Everyone says the sun is just an ordinary star, one of thousands. But here's the twist. No other star with the same parameters as the sun has ever been found. Its size, luminosity, temperature, age, everything about it is unique. Most importantly, the sun is remarkably stable. Its luminosity variation is extremely low, just 0.1%. This stability is vital for sustaining life. Do you know what happens when a star gets too big? It burns through its fuel faster and turns into a red giant. Yeah, the bigger the star, the larger its habitable zone. But there's a problem. The more fuel it burns, the quicker it dies. And guess what? It doesn't just fade away, it becomes a star killer. Look at Betelgeuse. It's nearing the end of its life with a lifespan of only 10 million years. Now compare that to our sun, which will live 500 times longer. Let's say it outright. Around supermassive stars, life doesn't even have time to develop. Everything burns up too quickly. But what about red dwarfs? Stars that not only outlive our sun, but endure entire epochs. A red dwarf with just 10% of the sun's mass can burn for 10 trillion years. That's practically eternity by our understanding of time. And as a bonus, red dwarfs never evolve into red giants. But these stars hardly shine at all. Their temperature is just slightly above that of a light bulb, around 5,400 degrees Fahrenheit. And they emit only 1/10,000th the light of the sun. For life to develop on such a planet, it has to be tightly bound to the star. But once the planet gets too close, it falls into a tidal trap, meaning one side of the planet will always face the star. Imagine this. One side of the planet is boiling, while the other is frozen in eternal ice. We can observe this kind of behavior with our natural satellite, the Moon, in relation to Earth. By the way, there are speculations about what might be on the Moon's dark side. Waiting for your comments, I have an interesting idea. Maybe it coincides with yours. And the cherry on top, the stellar wind. For these stars, it's just as intense as the solar wind, so even the terminator zone, the area between light and darkness, where the temperature could theoretically be comfortable, comes under threat. Now, let's take a closer look at the planets in our solar system. Does anything seem unusual to you? Could there be something odd about how they're arranged? And is this kind of layout typical for planetary systems across the universe? So, we've got 4 small rocky planets up front and then, bam! Giant gas balls right behind them. Seems normal, right? Like, pretty standard for solar systems? Well, not even close. Let me show you why. First off, just look at the range we've got. From teeny tiny Mercury to the massive giants Jupiter and Saturn. In most planetary systems, the planets are pretty much the same size. But not here. Nope. We went full-on unique. Most systems out there are packed with super-Earths. Huge, rocky planets several times bigger than ours. And us, we're stuck with these tiny rocks, and not even a single one inside Mercury's orbit. Secondly, gas giants like Jupiter and Saturn are real rarities. They're found in only about 10% of planetary systems, and even fewer have stable, nearly circular orbits that are also incredibly far from their stars. How this setup came to be remains a mystery. Scientists are still developing complex models, but they haven't reached a consensus yet. And now, the question, why do we have this particular configuration? Well, here's why. Earth is the perfect-sized planet. If it were smaller, it wouldn't be able to retain enough of an atmosphere, and the temperature on its surface would be extremely low and fluctuating, which wouldn't allow for the formation of oceans. On the other hand, If it were too large, it would have a super dense atmosphere. Let's talk about Venus for a second. Despite being smaller than Earth, Venus has an atmosphere 92 times denser, where temperatures soar to a scorching 864 degrees Fahrenheit. And here's the crazy part. Scientists believe that Earth might have once had a similar atmosphere, until a catastrophic impact changed everything. It gave Earth the atmosphere we have today. That's also how we got our celestial night lamp, illuminating dark nights for every living being on our planet. This is how we ended up with stable daily temperatures, an ozone layer shielding us from ultraviolet radiation, and carbon dioxide in just the right amounts. Together, these factors make life on our planet possible. We've strayed a bit from the topic, but just look at how the perfect configuration of planets in our solar system works in our favor. Gas giants on the outer edge? They act like a massive shield against asteroids. Take Jupiter, for example. I used to think it was just a bit bigger than Saturn, but actually, it's 2.5 times more massive than all the other planets combined. And that's why Jupiter is basically the bodyguard of our solar system. It can literally fling the hypothetical Oort cloud, with its trillions of comets, to the far reaches of the universe, protecting us from catastrophic collisions. Scientists believe that many of the objects in the Oort cloud may have once cozied up to the Sun, but then Jupiter, being the cosmic vacuum cleaner it is, along with its gas giant buddies, flung them into outer orbits during the solar system's early days. And now they're chilling far beyond Neptune's orbit, well out of range to bombard us. Jupiter doesn't just keep cosmic trash in check, it literally takes the punches for us. Take 1994, for instance. A 12-mile-wide comet slammed into it. If something like that had hit Earth, it would have wiped out nearly all life, basically hitting the reset button on evolution. And this isn't just a one-time thing. Jupiter literally scoops up all the cosmic wrecking balls that pass by. In 2009, one such rock even left a black scar in its atmosphere the size of the Pacific Ocean. This giant stands just beyond Mars. If its orbit were even slightly different, things could have gone very wrong for us. The solar system might look completely different, and most likely, we wouldn't even be here. Its orbit is so perfectly tuned that it sits right between two extremes, the biggest and the smallest planets in our system, without disturbing either of them. These fine-tuning adjustments played a critical role in making life on Earth possible at all. Remove any one of these factors, and we'd simply cease to exist. How many more hidden variables are at play influencing all this? We don't even know all the factors that helped shape our world. And this is just what's visible on the surface. Now, let's talk about Earth. Its core is much larger than that of most rocky planets. For example, Mercury, Venus, and Mars all have significantly smaller cores. And do you know why Earth's core is so big? It's all thanks to the Moon. Just look at Mercury or Venus. They don't have any natural satellites. And Mars? Phobos and Deimos aren't real moons, they're just captured asteroids, measuring only 14 and 7 miles across, respectively. But the Moon, that's a giant compared to them. It's the largest natural satellite relative to its host among the rocky planets in the solar system. It's a whole 27% the size of Earth. Pluto, which was once considered a planet, weighs 6 times less than the Moon. And what's interesting, the soil brought back by the Apollo missions looks suspiciously similar to Earth's crust. How did this happen? It all started with a massive collision. An ancient planet about the size of Mars, named Theia, crashed into Earth around 4.5 billion years ago. This impact created the Moon and gave Earth its huge core. The mantle and cores of Theia and Earth mixed during the collision, ejecting part of their combined material and forming our natural satellite. So, we're probably living on a mix of two planets. What does this give Earth? Well, for one, massive tides. Yes, it's the Moon that makes the oceans on Earth work. But here's the interesting part. Charles Darwin believed life first began in tidal pools formed due to tides. Also, the Moon's gravity helped life move from the ocean to land. But it wasn't as romantic as you might think. The Moon was much closer back then, and its gravitational pull was much stronger. Life was literally thrown onto land, where it died, until a useful mutation occurred. And fish literally ran across the beach. By the way, here's a cool fact about Earth's water. Back in 2019, scientists proposed that Theia could have brought water all the way from the outer solar system. Turns out our oceans might be cosmic travelers. The moon is so much more than just a satellite. According to Peter Ward and Donald Brownlee, it drives plate tectonics, which are key to biodiversity and the carbon cycle. Moreover, it functions like a massive dynamo powering Earth's magnetic field, which protects us from cosmic rays. Theia's impact gave Earth many of its unique features. For example, the planet's axial tilt and its fast rotation speed. These factors play a key role in maintaining stable temperatures and supporting viable photosynthesis. The most important factor is Earth's tilt. According to the rare Earth theory, if the tilt were too great or too small, life as we know it wouldn't be possible. A planet with too much tilt is like extreme seasons on steroids. And if it were zero, there'd be no seasons, which, strangely enough, would lead to a lack of evolutionary incentives. Without the moon, the tilt of our planet would be unpredictable, and life on land wouldn't be possible. The moon isn't just a satellite, it's a key stabilizer for life conditions. It helps maintain our climate and played a huge role in life moving onto land. Well, it may sound strange, but do you know the most paradoxical thing? Earth has experienced two global ice ages. The first one was 2.2 billion years ago, and the second one came much later, just 635 million years ago. And guess what? These terrifying cold periods actually acted as a catalyst for life. The first ice age wasn't just about the bitter cold. It paved the way for photosynthesis, meaning oxygen started filling the atmosphere and greenhouse gases began to decrease. The oxygen surge was the game changer that created our atmosphere. The second ice age marked a crucial turning point. It led to the Cambrian explosion, where all modern animal species began appearing abruptly. Before that, life was simple and single-celled. But afterward, a multitude of multicellular organisms started evolving at an incredible speed. And this marked the emergence of the first brain. Even if we find a planet with absolutely perfect conditions, chances are we won't find complex life there. Why? Because it wouldn't need to exist. On a paradise planet, there'd be no challenges, no survival struggles, and most importantly, no reason for evolution. For complex life to develop, balance is absolutely essential. It's not enough to just have good conditions. They need to be balanced with something harsh, so evolution can move forward. But here's the key. Negative factors must be just the right amount. Not too many because life is incredibly fragile, but if the balance is found, true growth can begin. So, what do you need for life to start on another planet? Let's assume we have the perfect planet. The right star, habitable zone, water, atmosphere, and even a moon. Everything you could ask for. And then what? Nothing. Without life, that planet will just stay dead. But for life to emerge, you need a starting point. It's a molecule that can self-replicate, a replicator. And until that happens, evolution simply can't even begin. And here's the hardest part. This first replicator had to come about by chance. Think about it. This complex system, capable of copying itself by serendipity, and yet, it has to be simple enough that chance could actually create it. But you know what? Even the simplest chemical combinations are incredibly complex for random occurrence. Ever wonder what the odds are for the first organism capable of reproduction to appear? The Russian evolutionary biologist Eugene Koonin, in his book, The Logic of Chance, presents this staggering figure. It's 1 in 10 with 1,000 zeros after it. Can you even begin to imagine that? Wrapping your head around this probability feels almost impossible. This number is so huge, it doesn't even fit on the screen when I use the smallest font size in my video editor. And here Koonin presents his theory. The multiverse. If there are infinite universes, then all possible combinations of atoms are infinite too. In that case, the appearance of a replicator becomes more plausible. But let's face it, it's easier to explain everything with the multiverse, or even with some kind of cosmic force. That way, your brain doesn't break. But Koonin reminds us that we need to minimize everything that can be explained differently, and the emergence of life is so unlikely that it leads to one conclusion. We're likely the only ones in this vast universe. Not just we, intelligent beings. We're living beings, and that's amazing. Because no matter how you spin it, the chance that life like ours could emerge anywhere else is incredibly small. I don't want to make it sound worse than it is, but it looks like we're about to face something unbelievably wild. Look, the first replicator appears, and it starts fulfilling its function of reproduction. The real question is, does evolution truly require complexity? The answer is, not necessarily. Look at the first replicators. Prokaryotes like bacteria and archaea, they were extremely energy inefficient. They simply couldn't accumulate enough energy for complex life. Evolution hit a dead end. Complexity couldn't arise through regular mutation. This was the moment when evolution completely stalled. For 1 billion years, just silence. No visible prospects at all. But then something incredible happened. What you could call a cosmic coincidence. An archaeal cell engulfed a bacterium and didn't digest it. It turned out to be so rare that, as biochemist Nick Lane suggests, it may have occurred just once in the entire history of life. The bacterium turned off almost all of its extra functions, focusing entirely on one thing: energy production. That's how the mitochondrion, the powerhouse of the cell, was born, and that's the beginning of everything. It's because of this tiny, incredible event that you're now listening to my thoughts and watching this video sequence, which has absolutely nothing to do with the topic of the video. And now, to the most important thing. Picture this: the number of intelligent civilizations in the universe. Let's put it in a formula. It's, simply put, the number of habitable planets, multiplied by the probability of life arising, multiplied by the probability of intelligence evolving. Here's the main point. Intelligence. Everything we've discussed so far doesn't guarantee that intelligence will emerge. And this is the crucial point we're witnessing right now. We've cataloged 1.7 million species of living beings. And honestly, that's just a fraction of all the life on Earth. Estimates suggest that our planet hosts around 9 million species in total. Over the entire history of life on Earth, there have been about 500 million. But how many of them developed intelligence? Evolution doesn't rush towards advanced thinking. And moreover, based on all the evidence we have, the emergence of intelligence is extremely unlikely. Charles Lineweaver, a researcher, argues that on the path to extreme traits in animals, intermediate stages don't always lead to what we might expect. For example, a large brain isn't an inevitable result, just like long trunks in elephants, or the elongated necks of giraffes. And here's the question: if dolphins are so smart and their brains are similar to ours, why, after 20 million years of evolution, haven't they built their own underwater cities? Why are we the only species on Earth to become intelligent? Why did evolution create such an overdeveloped brain in humans? After all, it's the same brain our ancient ancestors had just 10,000 years ago. Why did this excess appear if evolution had managed perfectly well without it for so long? What's the secret? We're not just smart, we're even overly smart. And here's how it happened. It's all about evolution working through chance and selection. Mutations plus natural selection gave us this giant, not entirely necessary brain, but it gave us the chance to start building civilizations. And here's the big question: how likely is it that we'll encounter intelligent civilizations in the universe? Honestly, it's like trying to win the lottery, even if your ticket is 1 in a billion. Look, we at least have a basic understanding of the factors that need to align for a planet to be habitable. But for life to emerge on that planet, let alone intelligence, that's a whole different story. Most factors needed for life to emerge are simply unknown to us. But let's take a moment to dream. Imagine we had a formula that guarantees the emergence of complex life, provided at least 10 factors align, some of which we've already discussed today. Let's make it even more optimistic. Assume each of these factors has a 50-50 chance, like flipping a coin. Let's say the chances of finding a star like the Sun are 50%. A rocky planet? 50%. Is it in the habitable zone? 50%. Does it have a moon like ours? 50%. You can keep going like this until you reach 10 factors. If it's that simple, then the chance of encountering intelligent life in such a universe would be 10 to the power of minus 24. or 1 in trillions of trillions. Simply put, the odds are so small that you could search the entire universe and not find a single planet like Earth. There are actually way more factors at play, and the likelihood of each one happening is far lower than we'd like to admit. So, when we say we're not alone in the universe, well, we might be wrong. Because as of today, we have absolutely zero proof of extraterrestrial life, let alone intelligent life. And now let's take a more critical look at the rare Earth hypothesis. Here's the first strike. While having a large moon is rare for planets in our solar system, it's not uncommon for planets in other star systems. This raises doubts about the idea that life couldn't exist without a moon. Furthermore, based on a 2008 study, scientists claim that Jupiter has actually triggered more collisions with Earth than it's prevented. So what role does it actually play? And the most surprising thing, the largest amount of water in our solar system is not on Earth. It's on Europa, Jupiter's moon. Yes, it contains twice as much water as our planet, even though its temperature is negative 275 degrees Fahrenheit. This is all thanks to Europa's orbital eccentricity and the effects of tidal forces. Beneath approximately 20 miles of ice lies an ocean that may reach depths of up to 120 miles. So, could life on Europa really be possible? Tardigrades on Earth live in extreme conditions. And on Europa, despite its icy shell, there could potentially be conditions for life. Life could exist on Titan, Saturn's moon, based on silicon, and even without water. Sounds strange, but it's entirely possible. Carl Sagan once hypothesized that life could exist on gas giants, where it might be based on ammonia, unlike the carbon-based life forms we know on Earth. Also, the rare Earth hypothesis claims that the Sun never crosses the spiral arms of our galaxy. But what do we see? The Sun actually crosses these arms every 100 million years. Some studies even suggest that several mass extinctions coincide with previous crossings of our solar system through the galactic spiral arms. By the way, the solar system is currently in such a crossing. Yeah, we're in the exact spot where mass extinctions might have occurred. And who's really unique here? Is it Earth? Doubtful. And here's another thing. The rare Earth hypothesis is an entirely anthropocentric approach. We're not just looking for civilizations, but civilizations that are like us. We still don't really know what intelligence is. Maybe intelligence doesn't have to look or think like us. We're looking for aliens who mirror us in every way. But maybe it's time to completely shift our perspective? So, what if silence isn't just silence? Maybe it's the answer to our question, and could there be something in that silence that stirs fear within us? The James Webb Telescope is currently exploring Europa's geysers. If we discover even primitive life, it could become one of humanity's greatest tragedies. Why? Stick around. Maybe I'll create an exciting video on this topic in the future. And if you're still here, that means you found this content interesting. Make sure you don't miss future episodes. Hit that subscribe button and give this video a like. Thanks for being here.